All right, let's get right into it. This is a deep dive for the pros, for those of us in the trenches of energy management. We're going to connect the dots, all the way from the bedrock electrical equations we all learned to the high-impact strategies that actually drive performance in the field.
And this is why it matters. Just look at that number. 45%. That's the slice of all global electricity that electric motors are eating up. It's a massive number, and frankly, it's where our biggest opportunities and our biggest responsibilities lie. Getting the math right here isn't just academic, it has huge financial and environmental consequences.
So here's our roadmap for today. We're going to start with a quick refresher on the core principles, the bedrock. Then we'll dive straight into the messy reality of AC power dynamics. After that, we'll scale up to the facility level, then zero in on motor efficiency. We'll see how all this math informs our key EMOs, our energy management opportunities, and we'll wrap up by looking at the future, data and verification. Okay, first up, the bedrock. Let's just quickly reestablish that universal language we all use, but let's look at it through the lens of energy waste. You know, everything we do traces back to good old Ohm's law, but we're not here to just recite the formula. For us, the key is understanding how this fundamental law shows up as waste in the complex systems we manage. So, V equals I times R. For us, this isn't about solving a simple circuit problem. It's about diagnosing real-world issues. Think about excessive voltage drop over a long cable run. That's Ohm's law in action, directly hurting equipment performance and, more importantly, piling up our energy losses. And from Ohm's law, naturally, we get Watt's law, which defines power. Now, all three of these equations have their place, but let's be honest. The one we really obsess over is P equals I squared R. Why? Because that equation is waste. It's the heat bleeding out of every wire, every transformer, every motor winding. We call them I squared R losses for a reason, and they are a direct hit to the bottom line. All right, let's leave the clean, predictable world of simple resistance. It's time to step into the reality of AC power, where the inductive loads that make up our facilities, all those motors and transformers, completely change the game. In the AC world, power isn't just one thing. We have to break it down. You've got real power, measured in kilowatts. That's the good stuff, the working power that actually turns a motor shaft. It's what you get billed for in kilowatt hours. But then you have apparent power, in kVA. That's the total power the utility has to send down the line to make that work happen. And the gap between those two, that's where our biggest wins are hiding. And this is how we visualize that relationship, the power triangle. It's probably our most important diagnostic tool. It shows us that apparent power, the kVA, is the vector sum of our real power, the kilowatt, and this other thing called reactive power, or kVAR. That's the non-working magnetizing power that inductive loads need to function. Our job, in a nutshell, is to shrink that kVAR side of the triangle as much as possible. Which brings us to our number one KPI for electrical efficiency, power factor. It's just a simple ratio of the work you're getting done, your kilowatts, to the total power you're drawing from the grid, your kVA. A low power factor is a huge red flag. It means you're inefficient, and it leads to utility penalty charges, it eats up your system's capacity, and it drives up those I squared R losses we just talked about. So it all comes down to this simple, elegant ratio. Power factor equals kilowatt divided by kVA. Getting this number as close to 1 as possible isn't just a technical exercise, it's a primary objective of any serious energy management program. It's a direct readout of how efficiently you're using electricity. Okay, so we've got the physics locked down at the circuit level. Now let's zoom out and apply these principles to the scale of entire industrial and commercial facilities, where we operate every day. In almost any facility we walk into, this is the money equation. The power in a three-phase system equals the square root of 3, our old friend 1.732, times the line-to-line voltage, times the line current, and critically, times the power factor. You absolutely have to have this calculation down cold to do anything meaningful, whether it's sizing new equipment or performing accurate measurement and verification. And of course, power is just a snapshot in time. What really matters is energy. Energy in kilowatt hours is simply your average power draw over a period of time. Power in kilowatts times hours of operation. This is the unit that shows up on the utility bill. This is what the client pays for. Now, let's get strategic. The load factor is an incredibly powerful metric. A low load factor means you have high peaks in your power demand compared to your average use. It's like paying for a 10-lane highway but only having a 10-minute rush hour. You're getting hit with massive demand charges for capacity you barely use. Improving your load factor is a direct way to cut costs, sometimes without reducing your total energy consumption at all. Which brings us right back to where we started, that 45% number. Let's really zero in on the prime mover, the electric motor, and talk about how we quantify the performance of the biggest energy user on the planet. This is how we get to the truth of what a motor is actually doing. The electrical power going in is equal to the mechanical power coming out to the load times that motor's specific load factor, all divided by its efficiency. This equation is how we cut through assumptions. It lets us spot underloaded, inefficient motors, and most importantly, precisely calculate the savings from an upgrade. All right, so now we take this whole mathematical toolkit we've built and we deploy it. We use it to identify and, just as importantly, to justify high-value energy management opportunities. Now, this list shouldn't surprise anyone, but look at it through the lens of our equations. Upgrading to a high-efficiency motor directly improves the efficiency variable. Installing a VSD is all about manipulating the load factor. Adding capacitors for power factor correction directly targets the PF variable to slash your kVE demand. You see, every one of these EMOs is a direct intervention in the math. That is how you build a rock-solid business case. And this isn't just random acts of efficiency. We apply these tools inside a structured process, like the motor performance management process. It's a logical, repeatable cycle. You evaluate what you have, you identify the waste using the calculations we've discussed, you analyze the opportunities, you implement the fix, and then, and this is key, you monitor and verify the savings to prove it worked. And that brings us to the final piece of the puzzle, proving our impact. Because the math can be perfect, but it's only as good as the data we feed it, and our ability to verify the results in a world that is getting more complex by the day. This quote says it all. Our equations are powerful, but they need good data. For the kinds of nuanced projects we work on, especially those with smaller savings margins or in facilities with highly variable loads, the monthly utility bill just doesn't cut it anymore. It's too blurry. Robust measurement and verification, or M&V, using granular interval data is no longer a luxury. It's non-negotiable if you want to prove your results. And this chart really drives it all home. It's a visual reminder of where the fight is. It reinforces why we are so focused on that massive 45% slice belonging to motors. But it also shows us there are still huge opportunities waiting for us in HVAC and advanced lighting systems. So I'll leave you with this question to think about. Our profession is changing fast. The old way of just analyzing a monthly bill is becoming obsolete. We are being flooded with real-time, granular data from smart meters and IoT devices. The challenge is no longer a lack of data, but an overabundance of it. So the question is, how will your M&V protocols evolve to not just handle, but to truly leverage this new reality to prove your value?